Today's daily code problem of the day is kth largest sum in binary tree number 2583. For this problem, we're given the root of a binary tree and a positive integer k. The level sum in the tree is the sum of the values of the nodes that are on the same level. So you want to return the kth largest level sum in the tree, not necessarily distinct. If there are fewer than k levels in the tree, we return -1. So two nodes are on the same level if they're the same distance from root. Basically, if we start at node 5 and then we go down to node 8 and 9 are on the same level. Nodes 2, 1, 3, 7 are on the same level, and nodes 4 and 6 are on the same level. So if we look down here, we're looking for the second highest value. So level 2 is a 17, level 3 is a 13, so level 3 is going to be our level 3 is going to be our answer with an output of 13. If we look here, k is equal to 1. We want to find the first highest value, which is going to be 3, simply because 3 is greater than 2 and 1. So for this problem, we're going to use a breadth first search, which means we're going to look at our left node, and then we're going to look at our right node, and we're going to use those to compute the sum between the two, and then we are going to add that to a priority queue. This priority queue is going to be a minimum heap. So our minimum heap is only ever going to contain a k amount of values, so we can keep track of which value is the kth largest value. So for the breadth first search, we're going to look at a left node, look at a left node, look at a left node, and then it's going to look at the right node, because a breadth first search is a way to traverse a binary tree by level. So it's going to always look at nodes on the same level, and it's going to come up here, then it's going to come up to 8, and it's going to look at 2, it's going to look at 1, but when it goes back to 8, it's going to go back to 5, go to 9, and then it's going to look at 3, and then it's going to look at 7, so that way we always get all the numbers on the same level. After that, we're going to, for each level, we're going to calculate the sum of their nodes. We'll keep track of the kth largest sums using a minimum heap, and at the end, the root of the heap will give us the kth largest sum. So the heap is perfect here because it allows us to maintain the kth largest element efficiently, as we'll only ever have to store k amount of elements. So let's jump into the code. First thing we're going to do is, if our root is equal to null, we will return -1. And that is simply because we are given the option that there could be fewer than k amount of levels. So there is the possibility where we don't have a root. Then we're going to return our breadth first search. We're going to pass it our root, and we're going to pass it k. So if the root's null, we'll return -1. Then we'll write our breadth first search. So let's go ahead and build that function right now. So we're going to have a private. It's going to return a long, and then it's going to be called our breadth first search. It's going to receive a tree node root and an integer k. So first thing we're going to do is instantiate a queue and a priority queue. So we're going to have a queue that's going to store tree nodes, queue, which is equal to a new linked list. We're also going to have our priority queue, which is going to store longs, and this is going to be our minimum heap. That will be equal to a new priority queue. Typically, when you're using a priority queue and you want to sort it, you'll define the function in these brackets so that it will be from least to greatest. In our case, we want the least value to be on top, so it's going to automatically sort to have our kth largest value at the top of the minimum heap already. We're now going to add queue.add our root, and this is simply going to allow us to keep track of what has already been stored in our breadth first, or what's already been traversed in our breadth first search. So now we're going to traverse each level of our tree. So while our queue isn't empty, we're going to have the size of our queue. So int size is equal to our queue dot size. And we're going to have a long level sum. So this is going to allow us to keep track of the sum of each level. And we will be able to add that to our priority queue. So to add the sum of each node at a level, we are going to have a for loop, which is going to pull whatever's at the top of our queue. And then it's going to look at all the children for that node. So for int I is equal to 0, as long as I is less than size, I can increment. We're going to have a tree node is equal to a queue.pull. And then we're going to level sum plus equals our node.value. So we're going to add the child nodes to the queue for the next level. If node.left is not equal to null, we can queue.add node.left, and if node.right is not equal to null, we will queue.add node.right. So in this for loop, we are going to traverse however many nodes are currently stored in our queue. Initially, it's just going to be our root. It's going to pull that from our queue, and it's going to add that to our level sum. After it does that, it's going to take the left node and the right node, and this is basically our base case. As long as a node is not null, it'll be added to the queue, and the queue will continue to do whatever it's doing. If a node is null, we won't add that node to the queue, and eventually the queue will run out, which will mean the queue is empty, and we will break our while loop. So in our minimum heap, again, we only want to maintain the top k elements in the heap. So we're going to have a min heap. We're going to add whatever the current level sum that was calculated is. But if our min heap dot size ever goes above k, we are going to min heap dot pull, as whatever we're removing from the minimum heap would be k plus 1. After this, we can simply return our min heap dot size. If it's equal to k, we will return our min heap dot peak. Otherwise, we will return -1. So this is a Boolean expression. Is min heap dot size equal to k? If so, we can return whatever's at the top of our heap. Otherwise, we're going to return -1 because there wasn't a k amount of rows. So this is it. If we run this, it passes our test cases, and if we submit it, it passes all of our solutions. So that's it. Thank you. Follow for more daily LeetCode solutions. I'll go through the code real quick if you want to stay and tag along. But that's it for this solution. So let's walk through what's happening here. Our breadth first search travel. We use a queue to traverse the binary tree level by level. Each time we finish processing a level, we calculate the sum of that level's nodes. So that's why we add our root first. So while queue is not empty, so queue starts at 1. We're going to have our size equal our queue size, which is 1, and our level sum is equal to 0. For each integer in our queue size, so just 1, tree node is equal to queue.pull, which is only going to happen once. Level sum is going to plus equal our node value. So it's going to be whatever our root node is. We'll then get the root node's child nodes, add that to our queue, and then we can add whatever our level sum is to our minimum heap. If the minimum heap ever gets bigger than k size, we can pull it. Because we just added 2 new nodes, this while loop is not going to break. It's going to say, oh, there's still 2 nodes. So it's going to redo the queue size, level sums back to 0, and then it's going to traverse each node and add it to our level sum. So theoretically, each row can increase in size. So we start with 1, and then we have 2, and then we have 4, and then we're going to be able to have 2, 4, 6, 8, so on and so forth. So adding the left and right of each node is going to ultimately build up to bigger and bigger and bigger and bigger trees. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth, until ultimately we are going to run into a null node. So 3 has 2 null nodes. It's not going to add to the queue, and eventually the queue will be empty. This while loop will break, and we can return our kth value. Thank you. Follow for more daily LeetCode solutions.